Okay, so yeah, I apologize. I had to cancel class last Wednesday. I wasn't feeling well. Um, but what I did is I posted supplemental videos for chapters 11 and 12. So uh, those are actually up right now. They do build a little bit off of quite a bit off of the hypothesis testing material we're talking about today, but they don't build directly off of correlation or regression, at least not to the extent that we really cover them. ANOVA is quite closely related in some ways to correlation or regression, but I don't think we're really covering either of them to the level of depth that we'll really see that relationship. So we can basically treat chapters 11 and 12 as kind of independent from each other, more or less, and from any of the chapter 10 material we'll be covering. So you could take a look at chapters 11 and 12 in the next, this coming week if you wanted to. Um, the plan for today is to continue with hypothesis testing, hopefully wrap up chapter 8 or at least get through most of chapter 8 Wednesday when we come back. So 2 days from now, we will finish hypothesis testing and start correlation and regression. And as I mentioned before, correlation and regression and ANOVA are really huge topics that that we could spend probably an entire course on either one of them, if not more than that. So we're really scratching the surface here. These last couple of topics, chapters 10, 11, and 12, are meant to be more expository, just introduce you to the underlying ideas, and not really an in-depth treatment of any of these topics. But the hypothesis testing in chapter 8 should be reasonably in-depth. You should understand it reasonably well for these tests when we are done with it. And then note that we do have a class meeting on Monday the 5th, so a week from today. We do have one last class meeting, so finals week really runs from Tuesday the 6th through the following Monday. It's always a little bit, offset like that because we either have Martin Luther King Day or we have Labor Day in the fall that kind of pushes everything by one day. So we do have a meeting on Monday the 5th on correlation and regression. However, note that the final exam will be available this coming Friday, so Friday the 2nd. Like I said, pretty quick turnaround after spring break this year. So it'll be available so that you can use the weekend if you want to, even though that's a couple of days before the official start of finals week. But of course, it's not due until Friday the 9th, so you are free to use that Tuesday, Wednesday, Thursday, Friday as needed. Like I said before, I'd strongly recommend planning to complete the exam, say maybe Wednesday or so of finals week at the latest. And that way, if anything goes wrong, you have a little bit of buffer. You can reach out to me. We can work out tech issues, anything like that. And note that it's not comprehensive, chapters 7 to 12. I'll post a little bit more or discuss a little more about the final in Wednesday's class. So that's the plan for the rest of the course. And the quote of the day for today, well, there's two quotes. The first is by Leopold Kronecker, and he said, God created the integers, everything else is the work of man. So essentially, I'm using this quote uh, as the summary, I suppose, of the side of this argument where when we're talking about mathematics, this is the work of man. In other words, it's something that is human created. On the other hand, there's a philosophy of mathematics, and I'm kind of summarizing that in Eugene Wigner's quote here. I'm probably horribly mispronouncing his last name, so I apologize to Eugene. But he has a paper titled The Unreasonable Effectiveness of Mathematics in the Natural Sciences. So I think, he would say something like there is evident an unreasonable effectiveness of mathematics in natural sciences. In other words, like we have some interesting physical phenomenon that we discover. We come up with a mathematical model to explain that phenomenon, and we expect the model to explain that phenomenon pretty well. But then we discover another kind of nearby in some loose sense phenomenon in the physical world that we didn't know about before. And our mathematical model actually describes it pretty well or does a pretty good approximation for that new phenomenon. We might not expect that, right? We would expect if we developed a model with this scope that it would only have that scope, and we discover something else in the physical world that we're going to have to back up to square one and make a new model to cover both of these things. But his argument is that, these models work better than we might expect them to. And this is really a debate in the philosophy of mathematics between mathematical formalism, which is mathematics is basically a game or something like that, that humans create the system of logic and we follow it to its natural conclusions. And, that of course it does a good job of explaining the physical world, because if I have 10 mathematical ideas and, one of them allows me to build bridges and the other ones just don't really seem to do anything of value, then of course the people who can build bridges are going to get paid more. There's going to be more incentive to go down that path than the other paths. So of course we do a lot more exploration of the paths that are more valuable for humans, which tend to be the ones that do a better job of describing the real world. And the other side is called mathematical Platonism, named after Plato, the Greek philosopher, where it's almost like these mathematical structures are inherently embedded in the universe somehow, and we're discovering them the same way that we like discover how gravity works. Gravity isn't there because we created it, or it doesn't work the way it does because we set an equation to it and said, this is how it works. It works the way it works. And whether we know about it or not, whether we have an accurate description of it or not, it's going to work the way it works. So I like to think of that as the kind of mathematical Platonism analogy, and something like chess as the mathematical formalism analogy. I've seen some people, some fairly bright people in arguments in philosophy, saying things like, well, you look at games that people invent, or language or something like that, and well, we have to, if we think of mathematics, we set out an axiomatic system and we don't know all of the conclusions in advance. We're still discovering what are the implications of, we set out these assumptions. What are the implications of those down the road? We don't know all of the theorems in mathematics. And some people say that that's evidence that we're discovering mathematics because we don't know the whole thing from start to finish. But I would argue that you look at something like chess, or maybe Go is another example, any sufficiently complicated game. I don't think anybody would argue that the rules of chess are fundamentally, baked into the universe somehow. We invented chess. I mean, I think if somebody were to argue that we didn't invent chess or Go, then it's almost like arguing we didn't invent. It would be hard to argue we invent anything then. But we certainly, the people who played chess 200 years ago didn't know about all of these consequences of openings or endgame theory or whatever that we know about today. The more you study these things, the more you learn about them. So that's kind of the mathematical formalism side of things. I tend to think of things more along the mathematical formalism side. I think that humans create math. It's an interesting game we play. We tend to explore the paths that align with the natural universe a lot more, because that tends to give us more lucrative rewards, right? If I can build somebody a bridge, they'll pay me to do that. If I just say, hey, I'm interested in, playing this interesting mental game with, number theory or something, harder to get somebody to pay you to do that. So anyway, that's kind of where I land, but there's a lot of very bright people that land in exactly the opposite camp. So, but I think it's interesting to kind of think about these two extremes, or, these two modes of thought, and also, how that comes into play in things like hypothesis testing and such, right? We're developing these statistical tests. Are these somehow like baked into the universe that this is the right way to do it? Or is it that we're saying this is one way to do it? I mean, it seems to work pretty well, like most of the time that we come to a conclusion based on a well-performed and well-analyzed hypothesis test. We don't substantially regret it later on when we discover new information. It's probably a true statement most of the time. But is this the only way to do it, or is this like the way that the universe like wants us to do it? I don't think so. I mean, we discussed that there are Bayesian approaches, there are other approaches as well. So, all right, with that thought, we will continue on with hypothesis testing. Okay, and since it's been a little while, let's do a quick recap. So recall the idea of hypothesis testing is we want to make a decision. We want to say we have two competing hypotheses. We call one the null hypothesis. We call it H naught, or we label it H naught, H subscript 0. And it's the one that gets kind of the benefit of the doubt. If the evidence comes up in kind of a gray area where we're not sure, we proceed forward under H naught. We presume that that's the true state of the world. However, if we can provide statistically significant evidence, if we can pass a pretty high bar with, say, like clear and convincing evidence or something like that, or evidence beyond a reasonable doubt, well, then we might switch from the null hypothesis to the alternative hypothesis. This is the thing that we're trying to show evidence in favor of. This is typically the thing that we want to prove, roughly speaking. I suppose as impartial scientists, we shouldn't want to prove anything, but in reality, there's always something that we want to prove. There's a reason we're doing the experiment, right? In our jury trial analogy, the null hypothesis was not guilty. So if the evidence comes forward and the person was in California at the time of the crime in Ohio or something, then we're quite sure they're not guilty. But if we maybe think that they're probably guilty, but we're not really too certain of that, we probably more than 50-50 chance they're guilty, but not enough to surpass that bar of beyond a reasonable doubt, we still determine that they're not guilty because we failed to pass that high bar to overturn the null in favor of the alternative and declare them guilty. However, if there is a lot of evidence and it's quite convincing and we're very sure that they're guilty, then we reject the null in favor of the alternative, we declare them guilty. So this presumption of not guiltiness, let's say, is kind of like the presumption of the null, unless there is so much evidence that it would be, in essence, in a loose manner of speaking, silly to dig in our heels and insist that the null is still true. It makes much more sense to switch to the alternative. We can make errors. We call the type 1 error rate alpha, and we call it the significance level. And the type 2 error rate is denoted by beta, and the power of the test is 1 minus beta. We mentioned that a perfect test would have both alpha and beta 0 or extremely small, but in reality, if we push one down, the other one pops up. So there's a trade-off between them. Okay, so let's take a look at developing a z-test for mu. So this is the first hypothesis test type that we're going to look at, z-test for mu. And here's our example. It's reported that the national average credit card debt is $3,262. A college believes their students have less credit card debt than the national average. They take a sample and they obtain the following information. And we looked at a few kind of extremes that could come out of this. But now we're going to go through the math and look at this particular sample information. So the sample they got is n equals 50 of their students with an X bar observed, an observed sample mean of 29.95. This is in the right direction. We're trying to claim that our students have less credit card debt than the national average, and 29.95 is indeed less than 32.62. But the question is it only a little bit less where it's kind of gray area? It could have easily have occurred just by sampling error, or is it so much less that it's unlikely to have occurred by sampling error, and we think that there really is a lower mean credit card debt for our students than the national average of 32.62? That is the question. We're presuming that we have a known population standard deviation sigma of 1100, and we want to make the claim at the 5% level. And we're going to look at 3 different ways to evaluate this hypothesis. We should come to the same conclusion in all 3, either reject the null in favor of the alternative or fail to reject the null and stick with the null. But the way that we'll get there and the intermediate information might be a little different between the three different methods. So let's first look at the p-value method. Okay, so well, we have our hypotheses, our null, and our alternative. We're making a hypothesis about the mean. So mu is our students' credit card debt, the population of our students, their credit card debt. And we would like to make the claim that mu is less than the national average of 32.62. That's the claim we'd like to make. So I'd like to provide evidence in favor of the alternative hypothesis, mu less than 3262. On the other side of the coin, mu can be bigger than or equal to 3262. Now, if you've read ahead a little bit, you'll see that there's a detail we might want to clarify here. We'll leave that. We'll leave it as is for a couple minutes, and then we'll see why we need to clarify that detail. So the detail with the inequality in the null, we'll clean that up in just a minute. Now, remember our little narrative, the guy with the flex time, and he does the investigation, right? And the skeptic and so on. So what we're trying to say is, what we're trying to look at is, okay, we have a sample. This sample is kind of, at a glance, something along the lines of more in line with the alternative hypothesis than the null hypothesis. The sample mean, x bar observed, is 2995, which is less than 3262. Is it so far less than 3262 that if the null was true, for us to get this sample, it would be extremely unlikely? That's the question. So the question is, roughly speaking, in the p-value method, roughly speaking, the question is, how unlikely is it to get such a sample, size 50, mean 2995, if the null was actually true, if the true mean, true population mean was actually bigger than 3262? So we always start our hypothesis test the same way. We write the hypotheses, and then we say, assume H naught is true. All of the calculations we do are under the assumption that the null hypothesis is true. And then we're going to look at something along the lines of how unlikely is such a sample if the null is true. If such a sample is very unlikely under the null and also more likely under the alternative, then we reject the null in favor of the alternative. If such a sample is not unlikely under the null, then we don't reject the null. Even if it falls on kind of the correct side, even if it's to the left of 3262, the sample mean, we still don't reject the null because it's not unlikely enough under the null. It's not enough evidence to surpass that high bar. That's kind of the gray area. Okay, so if we assume H naught is true, what can we say then? Well, if I look at the distribution of x bar by the central limit theorem, n equals 50 bigger than 30, so we can apply the result of the central limit theorem. X bar is normal with mean mu x bar equals mu, and standard deviation sigma x bar equals sigma over root n. Well, sigma x bar we can compute pretty easily. That is just our known sigma of 1100 over root 50. That's whatever that number turns out to be. And let me actually bring up the calculator. Might as well just get it started up. Bring up the calculator, and I might as well switch my screen share now as well. Because if I don't switch it now, I'll probably start typing on the calculator and you won't be seeing it, and I'll forget to switch it in a couple minutes. Okay, so what is our standard deviation for this normal distribution? Well, that is 1100. Oh, wrong window. 1100 over the square root of 50, or that's about 155. Or let's call it 156. What is the mean? Well, if H naught is true, then mu is bigger than or equal to 3262. Let's kick this can just a couple minutes. Let's come back to what we want to use as the center of this distribution. And let's kind of proceed forward, and then we'll come back and, correct this detail and this detail in a minute. But I want to develop the idea that we're going to go with here, proceeding forward, and show you kind of the logic behind the decision we're going to make to fix these two little issues we have right now. But we have some mean in the middle here. Probably something like 3262 or 3265 or 3300, something like that. I also have a sample mean, X bar observed is 29.95. Now, if I reject the null in favor of the alternative, if I say that my sample mean is low enough, it's far enough below 3262 that I reject the null in favor of the alternative. So I have 29.95 here. If I reject the null for 29.95, I certainly would also reject it for 29.94. That's even further away from the null and kind of more in line with the alternative, or 29.90. Or if I reject here, I'm going to reject anywhere else in this left tail. If 29.95 is far enough below 3262 to represent enough evidence against the null in favor of the alternative, then anything else, any other hypothetical X bar observed we could have gotten to the left of 29.95 would be even stronger evidence, so we'd still reject there. So we'd reject here if we reject for 29.95, if we reject for this sample. But keep in mind, we'd be rejecting H naught, but H naught is actually true. We'd be making an error here. We'd be rejecting a true null in this case. This would be our error rate, particularly our type 1 error rate. Remember, what is our type 1 error rate? Rejecting a null that is true. So if I rejected for 29.85, I would make an error, and I want to figure out what is the probability of this error. Probability of type 1 error if I reject on the basis of the sample that I got. So that is my big question. If this is a small probability of making an error, if I reject, then I'll reject because I don't make an error very often if I do reject the null in favor of the alternative. If it's a large probability of making an error if I reject, then I won't reject because I don't want to make errors too often. Okay, so I need a center to my distribution here to figure out to proceed. This is just a normal distribution calculation, right? But I need to know what the mean is. The issue that I have is up here, the null, the way I have it written, is mu bigger than or equal to 3262. So should I put like 3262 here? Or should I put like 3270? Or should I put like 3300 or 3500? What should I use as my center? What should I use as my mean here? Well, here's the thing. Let's consider 2995 to be fixed. If I set mu equal 3262 here, maybe this is what the picture looks like if I set mu to be 3262, the center of my distribution. What if I set mu to be like 3300 instead? Well, then I have the same shape for the distribution. I didn't change the standard deviation, but I would shift the distribution over to the right. If I use a mu bigger than 3262, that shifts my distribution over to the right more, but that makes this probability smaller. Remember, a small probability, a small likelihood of making an error if we reject, it kind of corresponds to reject H naught. But remember, we're giving H naught the benefit of the doubt. It's the default. We don't want to reject it flippantly. We want to have a good and solid evidence to reject it. So in other words, if I reject the 3300 and a mean of 3300 because this red area in the tail is pretty small, well, if instead I had centered the distribution at 3270 or 3262, that tail would get bigger. That probability of making an error would get bigger, and I might not be able to reject there. So if I center my distribution at 3300 or 3400, and I find that I can reject against that mu for the null, I might not be able to reject for null hypothesized mu's that are closer to 3262. But on the flip side, if I set my null hypothesized mu to be right at that borderline, 3262, that's the biggest that this tail can be, this red tail. if I can reject under basically the most favorable conditions for H naught, if I give H naught the biggest benefit of the doubt, if I say I'll set the null hypothesized mu right at the borderline, where the estimated error rate would be maximal, where that area in that tail would be as large as possible. If I can reject there for mu equal 3262, I could reject against the mu of 3300 or 3400 anywhere further out, because then the estimate for the error rate is going to be even smaller, and even I'd be even more able to reject. Okay, so where do we come down on this? Let me erase all of this blue stuff. Oh, it's not letting me erase anymore. Can I get rid of just, good, just that. Okay, so the thing is that the hardest null hypothesized mu to reject against is the one that's right at the borderline, right at 3262. So what we tend to do notationally is we write our null as mu equals 3262. And we make that the center of our distribution. Now this kind of like encapsulates all of the mu's bigger than or equal to 3262, but we don't write it that way. We have the null mu equal 3262, that's what we're testing against. And that lets us really pinpoint the center of this distribution right at 3262. Remember, if I can reject against this mu that's right on the border, then I can reject against any other mu that would be bigger than 3262. So again, I'm giving H naught the benefit of the doubt. I'm giving it the best chance to, in essence, win the argument. I'm picking for H naught the mu that's right on the border, that's the most favorable for H naught. It's going to make it the hardest to reject it in favor of H1. Well, now I can answer this question conclusively. What's the probability of the type 1 error rate if I reject H naught in light of this sample? Well, that's the probability that this normal distribution, X bar, is less than 2995. Right? My error rate is if I reject a true null on the basis of this sample, I make an error. That happens when my random variable X bar is less than 2995, or that's when Z is less than 2995 minus the mean of the distribution, which now we've concluded should be 3262, divided by the standard deviation of the distribution, 156, or 1100 over root 50. Let's figure out what that is. And 2995 minus 3262, all divided by 156 or so. So that's negative 1.71. Okay, give me 1 second here to pause my screen share. I just realized something. All right. Okay, screen share should be back now. I just realized that I had my student roster list up because I was answering student emails and so on, and so I didn't want to pop that up on the recording. Okay, so we need to find probability Z is less than negative 1.71, and as usual, we go to our Z table. We're looking for an area to the left of a negative Z score, so that looks good. We're looking for negative 1.71. That should be this one right here, negative 1.7 to the 10th place and 100th, so that is 0.0436. Or that's 4.36%. Remember, this is the probability of making a type 1 error if we reject the null on the basis of this sample. This is the thing that we call the p-value. So when we're talking about the p-value method up here, the thing that we call the p-value, I'm sorry that there are so many uses of the letter p in statistics, but this is our p-value. This is our probability of making a type 1 error, of rejecting the null, even though it's actually true in reality, if we reject on the basis of this sample. 4.36% of the time, we would make that type 1 error if we reject on the basis of this sample with X bar observed 2995, size 50. Okay, so that's all well and good, but what do we do with this? We need to come down with a binary answer. Should we proceed forward under H naught? Should we proceed forward under H1? Do we reject H naught in favor of H1? Do we fail to reject H naught? Which one should we go with? Well, that's where our last little bit of information up here, the 5% level of significance, comes into play. This 5% level of significance, we call this alpha. It's the maximum allowable type 1 error rate for rejection. So we're willing to tolerate an error rate of up to 5%. If I rejected for this sample, I would make an error 4.36% of the time. So I can say since the p-value of 4.36% is less than 5% alpha, or in other words, since the kind of actual type 1 error rate is less than the maximum allowed type 1 error rate. Since this is true, since our error is within the maximum allowable bound, we reject H naught in favor of H1. And what does that mean? That means we can conclude that the mean credit card debt for our college students is less than the national average. We can conclude mean credit card debt for our students less than the national average. So we can put this in our marketing materials and so on. And if somebody comes to us and challenges it and says, I don't think that's true about your students, show me the evidence, I would show them this sample information, and I would show them this logical argument. And I could say, I have given statistically significant evidence in favor of this statement at the 5% level of significance. Now, why do we choose 5%? That's a discussion that we'll have maybe next time, but the long and short of it is that everybody uses 5%. So because everybody uses 5%, everybody uses 5%, right? Like it's a status quo thing. People have been using 5% forever, so people continue to use 5%, which means that people will likely continue to use 5% for at least quite a while. All right. So that was our p-value argument. We say if I reject the null on the basis of this sample, what's my probability of a type 1 error? That's the p-value. And if that is less than the significance level, or alpha, the maximum allowable type 1 error rate, then we reject the null in favor of the alternative. If it's not, if this came out to be 7.36%, that would be, we'd actually encounter a higher type 1 error rate than is allowed. We would not reject the null. We would make an error too often, too high of a percentage of the time. We would not reject the null, and we would not be able to make our claim. So again, notice what we're doing here. We're really analyzing the well, first we're accepting the fact that X bar observed inherently has some sampling error in it. It's not going to be right on our student's mean. It might be a bit low, it might be a bit high, it might be really close to the population mean, but it is an estimate, it has some sampling error. 2995 is less than 3262, but the question is it less than 3262 just because we got a bit of sampling error? And this time that we did a sample of size 50, it was a little bit lower than usual, but that was just an anomaly. Or is it so far below 3262 that we'd say, I don't think this is just due to an anomaly. I don't think it's just due to sampling error. It makes much more sense for this to be due to something systematic, where our students' mean is truly less than the national average. And in this case, we ran the numbers and we said it was the latter, that we feel we've given statistically significant evidence that our students' mean is actually less than the national average. Now, be a little bit careful. What we haven't done, we haven't said like, we're very certain that our students' mean credit card debt is like really close to 2995. All that we really did is say this 2995 X bar observed with the surrounding information is evidence, is statistically significant evidence that the mean is less than 3262. Maybe it's 3260 or 3100 or something. Our best guess for our students' mean right now is 2995 because that's our sample mean. So that's still our best guess, but we're not somehow saying like we're really confident or certain or something that mu is 2995 or really close to 2995. We're saying that that we've provided evidence that mu is less than 3262. Okay, so we have another way of approaching this, and that's the rejection region method. So one way that we took a look at this is we said, let's look at our actual observed sample. And if we reject for that sample, how often do we make a type 1 error? And is that less than the maximum allowable error? This can be really nice if we wanted to say, test against maybe 3 different levels of significance. Maybe we like to know, are we significant at the 1% level, 5% level, and 10% level? That's something that you see often in, say, economics journals. They'll often take each data point and report, is it significant at the 10% level? Is it at the 5% level? And is it at the 1% level? So they often do all 3. In medical journals, it's usually 5%, end of story, it's significant or not. But so if I wanted to say, is it significant at the 1% level? If alpha was 1% instead, hypothetically, well, 4.36% is not less than 1%, so it's not significant at the 1% level. I could not make this claim at the 1% level of significance. But of course, 4.36% is less than 10%, so I could make the claim if alpha was 10%. If I want to compare against several different levels of significance, maybe getting a p-value is nice, because once I get the p-value, I've done all this work, I then only have to take this number and compare it against whatever my levels of significance are, 1%, 5%, 10%. If somebody decided to use 2.5% or something as a wonky significance level, doesn't matter. We just compare 4.36% against whatever alpha is chosen, and we get our answer. But now think of a different scenario. Maybe, I don't know, maybe I'm the world's most niche consultant, and I go around to all different colleges and I run the same experiment because, whatever, I think the colleges are very interested in knowing if their students have less credit card debt than the national average. So I go to University of Pittsburgh and I take a sample of size 50. I know the sigma is 1100. I get X bar observed for Pitt. Should I make the claim or not? I go to CCAC, do the same thing. Should I make the claim or not? I go to Carlo. Should I make the claim or not? Well, there, I'm making the claim at the making or not making the claim at the 5% level of significance every time. What's changing though is the X bar observed, right? At Pitt, I'm going to get a certain X bar observed. At CCAC, a different X bar observed. At Carlo, a different one. Wouldn't it be nice if I could write a number down in my pocket, or write a number down on a piece of paper, put it in my pocket? I compute X bar observed for this college that I go to, and I just compare that number, X bar observed, to the number I put in my pocket. We know that X bar observed further to the left, further below 3262, are stronger evidence to reject the null in favor of the alternative. And numbers that aren't very far to the left are weaker evidence. So can I come up with a cutoff number? Maybe it's like 3,000 or 3,010 or 3,050 or something like that. Can I come up with a cutoff number where I can say, I do this same sampling process, I just look at X bar observed and I compare it to a cutoff number. If the X bar observed I get is to the left of that cutoff number, I reject the null in favor of the alternative. If it's not to the left, then I don't reject. That's the idea of the rejection region method. Basically, what I'm saying is, what is the sample X bar observed, that is kind of the least amount of evidence where I can still get a rejection? What's the borderline X bar observed between rejecting or not rejecting? And then I can just compare my actual X bar observed against that cutoff X bar observed and see which side it falls on. That's the idea of rejection region. So for the rejection region method, we'll do the same initial step up here. I'll just copy this down so I don't have to rewrite everything, but we have our hypotheses. That's always the first thing we do. We read the problem, we understand the problem, we set up our hypotheses. Just like above, all of my calculations are done under the assumption that H naught is true, because we're looking for what's the probability that we reject given that H naught is true. It's a conditional probability. So if H naught is true, what's the probability I reject? That's the type 1 error rate. Reject the null given that it's true. So I assume H naught is true. I get my same picture as before. My distribution of X bar is normal. With mu X bar, remember, we're assuming H naught is true, so we also fix this and we put mu equals 3262 as our null. So we just have a 3262 here. We clarified that. And just like before, we had sigma X bar equals, was it 156? Yes, 156. Computed the same way as before. So I have my middle X bar index here, 3262. And I have some, maybe I'll do this in blue. I have some cutoff here. I have some cutoff, maybe I'll call it L. It's some like lower bound or something like that, where I say if X bar observed is less than L, reject H naught. And if not, do not reject. But remember, I reject H naught if probability of a type 1 error is less than alpha, or in this case, less than 5%. So in other words, I'll look at this area over here to the left. The biggest that area can possibly be, and I still generate a rejection, is 5%. So I want to figure out, basically what I'm doing is I'm asking an inverse question up here. I'm saying, what X bar observed would give me a p-value of exactly 5%? And that's the cutoff X bar observed. And then does 2995 fall to the left of it, so I reject, or to the right of it, so I don't reject? Well, really, I'm just looking for the 5th percentile of this X bar distribution. So what is L? Well, it's going to be the center, 3262, the mean of the distribution, minus, because we're on the left side, so minus a z-score, we'll come back to that, some number, times the standard deviation of this distribution, the standard error, 156. I'm looking for a z-score with 5% area to the left, I see that's one of my little special cases down here. My z-score with area 5% to the left is negative 1.645. So this is 1.645. The negative essentially is what I have out there as the minus. Okay, let's bring up the calculator. So I need 3262 minus 1.645 times 156. That looks right. So this gives me 3,005 and 38 cents. So this is my rejection region. I write $3,005.38 on a piece of paper, put it in my pocket. I go to Carlo, compute their X bar observed. If it's less than 3005.38, we reject the null in favor of the alternative. I go to their administration and say, hey, you can make this claim about your students. If it's bigger than 3005.38, then I don't know, you know, run away and do something else or something, because we can't make the claim then. We haven't given enough evidence in favor of the claim. So then I ask, is X bar observed less than 3005.38? Well, X bar observed is, what was it, 2995, right? Yeah, 2995. That was from our sample all the way up above, which is less than 3005.38, or my lower bound. This is true, so I do reject 8 not in favor of H1. Oh, in favor of H1. And just like above, I can make my claim now. So I get the same end result. But what's the difference? Well, up here, if I had several different significance levels that I wanted to test against, it was easy for me to test against them, the 1%, 5%, 10% level, because I just compare 4.36% against each of those numbers, and it's very easy to tell whether it's significant or not at the different levels. If I change alpha down here, every time I change alpha, that changes Z, which changes L. I have to do a bunch of work for each time I change significance levels. But if I change X bar observed, if I went and did this to 10 different colleges and got 10 different X bar observed, I'd be able to tell just with evaluating an inequality for each one of them whether it's significant or not. Right? If I change X bar observed up here and move 2995 to the left or to the right a little bit, that changes my p-value. I have to recompute my p-value for every new X bar observed in the p-value method. But in the rejection region method, if I have different X bar observed, different values of X bar observed from different samples, different scenarios, I can just compare them to 3005.38 and tell right away whether I get significance or not at the 5% level. And then the third method is a little bit like a bit of a mashup between the two. It's called the critical value method. Most of the time, we're going to be solving or performing these hypothesis tests for chapter 8. We'll be using one of these two methods. But critical value method becomes very important in things like the ANOVA test or the ANOVA, analysis of variance, and the test that comes along with that, or like the chi-square tests. So the critical value method is very important there. So we're going to look at it in this context where things are a little bit simpler. And essentially, we're going to kind of, in a sense, blend these two methods. So here I was looking to establish a rejection region in terms of like dollars, right? Like this is in dollars. 156 and 3262 are in dollars. So I was looking to establish a rejection region, but kind of on the basis of the original units of the data. Up here, I see that what came out kind of naturally as I went through my process was I converted my X bar index into a Z-score. what does this z-score look like? It looks like x bar observed minus the null hypothesized value of mu, I'll write that just as mu subscript 0, over the standard error. That's kind of like my z observed. That's the z-score related to the observed value of x bar, related to this index 2995. So I can think about establishing a rejection region, but not in terms of units of the original data, right? That can be a little bit finicky, a little bit annoying to work with, but maybe I establish a rejection region in terms of this kind of unitless uh, characteristic here, this z observed. Okay, so again, can I just control V? Is that still? Oh, nice. All right, that's still there. So again, and just to be clear, I want to be clear about something. If this was on an exam or something and you solve this with a p-value method, you write your answer, and at this point, you're done. You've got the answer. Move on to the next problem, right? If you're on an exam, if you're pressed for time, don't solve all the problems 3 different ways. But if you're looking for a little bit of practice, we're looking at throwing different tools in the toolbox here. If I solve a certain problem using, say, a p-value method, maybe ask yourself, well, what would a rejection region method look like for this? Try to run through a different angle of attack and see if you can get the same answer. So for practice or homework or something, that's a good that's good practice. But for an exam, like we could do a p-value method, get the answer, we'd have the answer, reject or don't reject. We could do rejection region method, we'd have the answer, reject or don't reject, right? You pick whichever one works best for that problem and you do that one. Okay, and then critical value, again, this is a third separate method that we should get the same answer at the end, reject the null in favor of the alternative. But we'll see that the process is slightly different. Just like before, we'll assume H naught is true. Because we're looking to control the type 1 error. We're looking to control the probability that we reject a null that is true. And here we're going to write out a critical value. We're going to write out z observed is x bar observed minus the null hypothesized value of mu over, well, this is going to be sigma x bar. This is sigma over root n. This looks very familiar. This is what we call the, well, this is related to what we call the critical value. We figure out z critical. We'll get a number for this. We'll get a number for this. And then we'll compare the two. Essentially, what we're doing is we're getting a rejection region just like up here, except our rejection region, instead of being in the x bar world, our rejection region is in the z world. Centered at 0, we have some z critical, we have some z observed, and since, in this case, since z observed is to the left of z critical, we'll be able to reject. So what is z observed? Well, that's our x bar observed, 2985, minus the null hypothesized value of mu, 3262, over sigma over root n. Remember, that was what turned out to be 156. And we did this above, remember, all the way back up here. We already did this calculation, and we got negative 1.71 for that number. So this z observed, this is the z-score related to 2995 over here. That gave us a p-value. And remember, we reject if the p-value is less than alpha, the significance level. So here's where we kind of switch mentality a little bit to a rejection region. We now ask, well, if the z observed, if it's way far to the left, it was like -5. Yeah, we can reject. If it's 5 standard deviations below the mean, we can reject without a second thought. If it's -1.7, I'm not sure. That's kind of close. We need to actually do the math. What's the borderline z number? Is it -1.7 or -1.6, -1.5, -1.9? What's the borderline z number where I switch from not being able to reject to being able to reject? That's my z critical. In this case, this is going to be the 5th percentile of z. Right? Or in other words, it's going to be P5. What's our 5th percentile of z? We actually found that already, right? That was -1.645. So we're blending kind of a little bit the ideas from the p-value method and from the rejection region method. Or really what we're doing is just rejection region method in the z world. But we see that this is -1.645. That is the z index with 5% area to the left. If our z observed has less than 5% area to the left, p is less than 5%, p is less than alpha, we reject. And that happens if and only if z observed is to the left of z critical. So we say since z observed is to the left of z critical, since -1.71 is less than -1.645, we reject H naught in favor of H1. And we can make the claim that our students have less credit card debt than the national average. Now, there's a detail that I would like to go back through and take a look at. What if we were trying to make an argument that kind of, in a sense, pointed in the other direction? What if I wanted to make an argument that like graduates from our program like earn a higher monthly salary than the national average? Maybe the national average is 3262. So what would happen if my alternative hypothesis was mu bigger than 3262? How would things change? Let's look at this inequality, p-value compared to alpha. Would this inequality change? Well, no, because the p-value is always the actual observed type 1 error rate. And that error rate, the observed error rate, I always want to be lower than the maximum allowable error rate. So that inequality, p less than alpha, is going to be the same regardless of which direction the alternative hypothesis inequality points. What about this inequality? This one will change because now evidence in favor of our students making more money than the national average occurs when X bar observed is way to the right. So these inequalities will change. This one will stay the same though. P less than alpha is P less than alpha no matter what. But when my alternative hypothesis is mu bigger than, then I'm going to be looking for X bar observers that are far to the right to provide evidence against H naught in favor of H1. What about this inequality? Or this one, or this one? These will all change. Because now I reject H naught in favor of H1 if X bar observed is way to the right, if my students are making a lot more money than the national average. This will change. This will change. So anything related to the indices is going to change, but things related to the probabilities are not going to change. And then similarly, if this becomes a bigger than, what changes over here? Well, the main inequality here is this one, and this does change because again, I'd be looking for X bar observes and therefore Z observes way to the right. So I'd be looking for a large positive Z observed. So we have names for these ideas. The original one that we did, where we were looking at mu less than 3262, we call this a left tail test. And in particular, it's a one tail test. It's a left tail test because all of these tails that we're looking at, all of these areas we're looking at, here or here or here, are left tails. If we switch the inequality, that basically just flips the geometry everywhere. So if my alternative was like mu bigger than 3262, then all of those left tails look like right tails instead. They flip over to the right side. I have a right tail test then. It's still a one tail test, a little bit more like a one-sided confidence interval kind of, right? You might have recognized this formula here from the one-sided confidence interval formula or just confidence intervals chapter in general. But if I had mu bigger than for the alternative hypothesis, this would be a one tail test, but a right tail test. So there's a little bit of a nuance there. So you need to be careful with the direction of the alternative and ask yourself, what types of X bar observers would be strong evidence against the null and in favor of the alternative? If the alternative is mu less than 3262, I want X bar observers that are very low, very far to the left of 3262 to provide evidence in favor or against the null in favor of H1. Or if my alternative was mu bigger than 3262, I want X bar observes that are much larger than 3262 to provide evidence in favor of H1. Okay, let's look at our next example here. So example 2, a quality control engineer is working for a food company. Let me zoom this in a little bit. For a food company, they're assessing a juice dispensing machine. The machine is supposed to fill bottles with 16 fluid ounces of juice. So that's what they put on the label, 16 fluid ounce. And in this case, it's bad to overfill or to underfill bottles. If we overfill, we're giving away free product and potentially even creating a mess when our customer opens the bottle. Maybe it goes everywhere because it's overfull. But if we're consistently underfilling bottles, that's also not good. We're cheating our customer out of product. We're giving them less than we're telling them we're giving them. Ethically, obviously, that's not good. But even if we weren't concerned with ethics, we're probably concerned about regulatory bodies, or our competitors are probably buying our product and testing it and kind of keeping us honest. So we don't want to overfill and we don't want to underfill. If there's strong evidence that true mean fill volume is no longer 16 fluid ounces, if it's different than 16 fluid ounces, then we'll take the machine offline, recalibrate it. And here is our question. Based on the following sample data, is there statistically significant evidence at the 5% level that the true mean fill volume is different from 16? And this is the key wording here. And we might also want to look at the 1% and 10% levels, just as practice. And here's our sample. We have a sample size 10. We're assuming normality here, so we can apply the results of the central limit theorem with no problem. X bar observed 15.92, sigma equals 0.10. We're given population standard deviation. But note the difference here from the previous one, right? Previously, we were looking to argue that our students' credit card debt is less than the national average. So if we got an X bar observed that was very low, that's strong evidence in favor of the alternative of the claim we're trying to make. But if we got a very large X bar observed, if we were trying to show mu less than 3262, but we got like X bar observed at 3500, well, then we clearly don't have evidence in favor of the claim we're trying to make. But here, I think the mean is 16, If I get an X bar observed that's way to the left, then it seems I'm underfilling. It seems the mean is no longer 16, and I shut down the machine and recalibrate. But also, if I get an X bar observed that's far to the right, I do the same. I reject the null in both cases if X bar observed is way to the left or if it's way to the right, because either one of those sides would indicate a difference from 16 in the mean. We call this a two-tail test because we'd have evidence in favor of the alternative and against the null in either side, if we were far to the left of 16 or far to the right of 16 and X bar observed. Okay, so like usual, we start by writing our hypotheses. We're making a set of hypotheses about the mean. And the question is, the alternative hypothesis is, well, is mu different than 16? In other words, is mu not equal to 16? So we don't have a less than here or a greater than here, we have a not equal to. The null then is mu equals 16. And this is actually the null. There's no other like fixing things or anything like that. There's no like this is mu equals 16, but it kind of incorporates or encapsulates all the other ones. There's mu equals 16 for the null, mu not equal 16 for the alternative. Just like before, we'll assume that H naught is true to make our calculations, because our question is ultimately we want to find the p-value, the probability that we reject the null, the probability that if we reject for this sample, that we reject a null that is actually true. And again, I look at my distribution of X bar by the central limit theorem. Remember, we assume normality here. So even though we have a small n, we still can apply the conclusion of the central limit theorem. Mu X bar, well, assuming that H naught is true, that's going to be 16 for the mean. And what's sigma X bar? That's sigma over root n. That's 0.10 over root 10. And let's see what that is. So 0.1 over the square root of 10. So that's about 0.032. We have an X bar observed. Oh, let me write my mean here. This is 16 right in the middle there. We have an X bar observed of 15.92, so that's a bit to the left. If I reject on the basis of this sample, this X bar observed is 15.92, I'd also reject for 15.91 or 15.9, anywhere further to the left here. Right, if I were to reject for 15.92, if that was far enough away from 16 for me to reject the null in favor of the alternative, anything farther away on the left, 15.9, 15.8, would also be would be even stronger evidence, would also be enough to reject. So here I reject H naught, even though H naught is true, I'd make an error, a type 1 error. So just like above, I start with p-value equals the probability that, I'm leaving a little space there, probability that, well, what, my random variable X bar is less than 15.92. But one thing I might realize is, okay, so if I reject for 15.92, I would get even stronger evidence, or at least as strong evidence, if X bar observed was 15.91 or 15.9 or so on the left. But this is actually a two-tail test. So in other words, if I was 0.0, if I rejected for 15.92, I would say I'll reject if I'm 0.08 fluid ounces below or more. But there ought to be symmetry in this, right? If I'm going to reject for 0.08 fluid ounces below, I have just as much evidence that mu is no longer 16 if I'm 0.08 fluid ounces above 16. Or if I'm 0.09 above or 0.1 above or anything further to the right. I don't really want to think too hard about this because, right, if I try to do this area plus this area, I've got to figure out what this index is, and that's kind of messy. But I note that by the symmetry of the argument and the symmetry of the distribution, I actually can just pop a 2 in here. This area is the same as that area. For a two-tail test, when I'm computing my p-value, I just have 2 times this probability because I have one of these probabilities on the left, but another one on the right that's mirroring. Because if I would reject for 15.92, 0.08 below, I should also reject for 0.08 above at 16.08 or higher. But from this point forward, it's pretty routine. So you get a z-score, 15.92 minus the mean of the distribution, 16, over the standard deviation of the distribution, 0.032, where that's twice the probability z is less than. Let's figure out what this is. This is going to be 0.08, or I suppose negative 0.08. We'll put the negative in, but 0.032, or that's 2.5. So we need to figure out what's the probability z less than negative 2.5, and then we need to multiply by 2 to account for the fact that if we reject for 15.92, we'd reject for all of the x bar observed to the left of 15.92, but also for all the x bar observed bigger than or equal to 16.08. Okay, so let's bring up our normal table here. We're looking for the probability that z is less than negative 2.5, and that's right here, 0.0062. Or that's 0.62%. So this is 1.24% when I multiply by the 2. My p-value is 1.24%. In other words, this is kind of, this is saying if I reject for x bar observed, this is my kind of like observed type 1 error, my actual experience type 1 error rate. And so I say since my p-value, often we just call this p, and we might just say since p equals 1.24%, but I'll write it out because we use the letter p for everything, so writing it out makes it very clear what we're talking about. Since my p-value is 1.24%, remember my significance level was 5%, at least initially here. How does this compare to 5%? This is less than alpha 5%. Or since my something like experienced type 1 error rate is less than the something like maximum allowed type 1 error rate, since the experienced error rate, if I reject it, is less than the maximum allowed error rate, then I reject. So we have provided at the 5% level statistically significant evidence that the true mean fill volume of this machine is no longer 16 fluid ounces, and we should shut it down and recalibrate. We don't want to shut it down flippantly, right? If we see an X bar observed that's 15.99 or something, we don't want to say, oh my, it's not exactly 16. We should shut it down and recalibrate. Our machines will always be offline. But if we have evidence that the mean is no longer 16, if X bar observed is far enough away from 16 that we don't think it's just due to a bit of sampling error, well, then we shut down and recalibrate, get things back into spec, and bring it back online. how would this compare to the analysis for, say, the 1% and the 10% levels? Well, for alpha equals 1%, my p-value of 1.24%, is that less than my alpha of 1%? No, it's not. That's kind of a very big no line. No, it's not less than 1%. My p-value is not less than alpha. My experience type 1 error rate is, in this case, bigger than the maximum allowed type 1 error rate. So do not reject H naught. Do not take the machine offline. There's not quite enough evidence if we were at the 1% level for significance to argue that it's out of spec. If alpha was 10%, my p-value is 1.24%. Is that less than 10% for alpha? Is it true that 1.24%, the experienced type 1 error rate, is less than the maximum allowable error rate if the max allowable was 10%? And yes, that's the case. So we can reject H naught in favor of H1. We can conclude that the mean fill volume is no longer 16 fluid ounces and shut down the machine and recalibrate. Any questions on any of this? Okay, so I've mentioned this a couple of times, but all of the math, all of the calculations we're doing here should look very familiar from mostly from chapter 6, a little bit from chapter 7. What's really challenging about hypothesis tests is what is the logic? Why are we doing which calculations in which areas, right? And what does the result of that calculation actually tell you? So that's the challenge for hypothesis tests. It's not so much the mathematics of the calculations and crunching the numbers, it's more what calculation should I do? And when I get the output of that, what does that actually tell me? How do I use that number to decide for H naught or H1? Okay, so let's look at moving on to the t-test for mu. Let's look at a different hypothesis test. It's going to work pretty similarly to the z-test for mu, but slightly differently. Let's look at this example. A city would like to advertise the average commute time to work in their city is less than the national average. So maybe this is promotional material saying, hey, our city is nice, you should come to our city. The national average commute time to work is reported to be 25.4 minutes. The city takes a sample of size 25 and computes X bar observed is 22.1 and S, the sample standard deviation, the 5.3. So as we might have guessed, the t-test for mu, kind of like the t-interval for mu, it works basically like the z-test for mu or the z-interval for mu, but when we're estimating S as well as, or when we're estimating sigma by S as well as mu by X bar. We'll assume the commute times to work are normally distributed, so we can use the results of the central limit theorem. And the question is, at the 10% level, can the city make the claim? So here, let's do this in the rejection region method. Rejection region. Okay, so we always start out by writing out our hypotheses. We're making a claim about mu, right? We want to make a claim that the average commute time to work is less than the national average. So mu will be this city's true population mean commute time. We don't have access to mu. If we did, we would just say this is mu. Is it less than 25.4 or not? And we'd make the claim based on that. But we don't have that. We have access to a sample. But we're trying to argue that mu is less than some number. So we want to provide evidence for mu being less than some number. So that's our alternative hypothesis, mu less than some number, which makes our null mu equal some number. The number we're comparing to is the national average commute time that's reported to be 25.4. And remember this null mu equals 25.4 kind of encapsulates all of the mu's bigger than or equal to 25.4. If I can reject against a null of 25.4, I could reject against any other potential null hypothesized mu bigger than 25.4 as well. So again, I'm giving the null the benefit of the doubt here. What types of X bar observed would give me strong evidence against the null and in favor of the alternative? Well, X bar observes that are very low numbers. If I got an X bar observed of like 10 or 15 or something like that, that would be really strong evidence that the mean is not actually 25.4, but is less than 25.4. On the other hand, if I got an X bar observed of 30, that would not at all be good evidence that the mean is less than 25.4. And what would a gray area look like? Well, maybe if I got an X bar observed of like 20 or 22, it's kind of on the right side of things. It's less than 25.4, but is it only a little bit less that could just have happened due to sampling error, could reasonably have happened due to sampling error? We just happen to get in our sample of 25 a few extra folks who have a short commute. Or is it unlikely to have just happened by sampling error and we can attribute it to something systematic, that the mean is, or that we can conclude that the mean is less than 25.4. So that's the question here. As usual, we'll assume H naught is true. And we'll make our calculations. So again, I want to think about my distribution, but in this case, instead of a z, it's going to be something like a t distribution. I'm kind of putting quotes around the t here because t distributions are always like standard in a sense. They always have mean zero, but to draw an analogy with the z-test for mu, this would be like a quote t distribution where the center is at 25.4 and where we have a left tail test. So I'm looking for a lower bound that has, well, what's my level of significance? Alpha is 10%. I'm looking for a lower bound with 10% area to the left. Or I know that that lower bound L is going to be, well, it's going to be 25.4 and minus some t value. Now it's not quote t, now it's actually t. So 25.4 minus some t value times Sx bar. Or this is 25.4 minus some number that we'll look up on the table times S over root n. 5.3 over, and my sample was size 25, n is 25. So over root 25. So this is my lower bound, or this is my cutoff between rejecting and not rejecting. So if X bar observes to the left, we reject. If it's to the right, do not reject. What should this cutoff be? Actually, let me pause my screen share for one more second here. Get my t table sorted out. There we go. Okay, so I have my t-table, and I know that I'm looking for a one-tail area of 10%. So I'm looking for a one-tail area of 10%. So I'm looking down this column. I do remember, though, that, remember, there's kind of, in a sense, like lots of standard t distributions for different degrees of freedom for basically different sample sizes. Which t distribution am I working with here? Well, I'm working with the t distribution where the degrees of freedom is n-1, just like in the confidence intervals section, or degrees of freedom of 24. So n-1, just like before, degrees of freedom 24. So I'm looking for area in one tail of 10%. It's because I have a one tail test, a left tail test, with an alpha and error rate of 10%. And I'm looking for that number for a t distribution with 24 degrees of freedom. Or in this case, that's 1.318. So I need to go 1.318 standard errors below 25.4. Let me bring up the calculator. So 25.4 minus 1.318 times 5.3 over, and root 25 is just 5. So we'll just type that in like that. And that's 24 basically right on the nose. This is my cutoff. This is the boundary of my rejection region. And I can say if X bar observed is less than 24, remember our X bar observes to the left are the ones that give strong evidence to reject H naught in favor of H1. We reject H naught in favor of H1. Or if X bar observed is greater than or equal to 24, we fail to reject H naught. Do not reject H naught. In this case, looking at our sample, X bar observed is 22.1. So I would say since X bar observed is 22.1, which is indeed less than 24, our L, our cutoff for our rejection region, reject H naught in favor of H1. And we can make the claim at the 10% level of significance. So we can put this in our promotional materials if the neighboring town says, hey, I think you said this in your material, but I don't think it's right. I think you're, lying or mistaken or something like that. We can show them this sample data along with this argument and say this is our evidence in favor of our statement. Now, the next town over could say, well, why did you use the 10% level? You should have used the 5% level, right? You have to pick a level of significance to use, and which level do you pick? That's not an easy question to answer. In some cases, like say the medical field, there's a very established norm of 5%, like everybody uses 5%. In some cases, like I mentioned, a lot of economics journals, they just report all of them, 10%, 5%, 1%. It's like, well, you take your pick, what you think, counts in a sense as strong enough evidence. So why did we choose 10%? Well, hopefully we would have some rationale for choosing 10%. As a little side note, it would be unethical and frankly just bad math and bad statistics for us to say, like, do something like go through here, figure out what P is, and then go back and decide what we want alpha to be to make it significant, right? If I ran my numbers, got a p-value of 7%, and then said, okay, I'll choose the 10% level of significance because 7 is less than 10, and that makes my experiment look significant. That makes my results look significant. That would be not only unethical to do, but also just kind of bad math because we'd be choosing alpha based on p. That's not the way that the flow of the logic works. So at the outset of the experiment, ideally before we even collect the data at all, we would say, this is the level of significance that we're going to use for our interpretation. We decide that in advance. We would hopefully have some rationale for choosing that. And then we would collect the data. We would find the p-value, compare it to alpha, or develop our rejection region on the basis of this 10% level or whatever we picked, and decide whether we can make the claim or not at that level. Something else that I want to mention that's important is if we get a rejection like this, we reject H naught in favor of H1, we've not proven that H naught is false and that H1 is true. We've given statistically significant evidence against H naught in favor of H1, but we're still admitting in this case, where was it? We're still admitting a 10% error rate, right? Like 10% of the time that we say H naught is true and that we say H naught is false and H1 is true, 10% of the time we'll be incorrect in that, and H naught will actually be false. So we haven't proven in the sense of like a mathematically rigorous proof. We've provided evidence in favor, is really what we've done. We've given evidence in favor of H1 against H naught, but a perfectly reasonable person could come by and say, I think a 10% error rate is too high. Maybe the industry standard is 5%, or I'm only comfortable with a 1%. And maybe they would have a different point of view on what alpha should be. We can't drive alpha to zero. We can't make alpha zero because then we would never get a rejection. So, right, we would need, if we made alpha zero, we'd have our lower bound equal negative infinity in some sense, and we could never get an X bar observed below negative infinity to get a rejection. So all that we can really do is provide evidence. There are some people, particularly the very hardcore math folks, who really don't like that idea. They want to know that, if you do a mathematical proof in algebra or calculus or something, like it is true 100%, no argument. They like those kind of situations. But when you're dealing with real world situations, real world data, I mean, nothing is ever true 100% in the real world, right? So we're stuck with what feels like it feels a little bit like we're saying nothing because we could always be wrong. But if you take a look at if 20 or 100 or 1,000 of these studies are performed under these scenarios, and if they're well performed, well analyzed, well reported, and so on, is science moving forward or is science moving backwards, right? Are we learning new things? And when we learn something new and we say we're confident that this is true, are we constantly having to backpedal and say, oh, wait, well, actually, that's not true, and significantly change our statement? There's always going to be clarifications or nuances or, minor modifications that have to be made. But, Newton's law, F equals ma. I mean, yeah, we have, quantum mechanics now and different gravitational theories, the theory of relativity and so on, that bring some other nuances to F equals ma. But F equals ma is still a heck of a good approximation for most of the stuff that we care about on a daily basis. So it's not like we developed F equals ma and said, oh, wait, that's completely wrong, right? That was what happened back in like the days of the ancient Greeks, like Aristotle's F equals mv, basically. You have to keep pushing something to keep it moving. And then Newton says, no, wait, F equals ma. So that was a pretty significant revision, but we're not overturning F equals ma, right? So that's really the argument here. It's an argument of evidence in favor or evidence against. It's not a conclusive, mathematically rigorous proof that one or the other is right or wrong. Right. And I mean, if you think about it, like we're trying to say something about a population on the basis of a sample, like there is certainly unknown information out there. Even if our sample size was 1 minus the size of the population, we still couldn't say conclusively, at least not in most cases. The last data point that we're missing could be a crazy off the wall data point and change everything. Okay, so when we come back, we will maybe do another example in the t-test, talk about z-test for proportion, and wrap up our discussion on hypothesis testing. So that's the plan for Wednesday. And then maybe start correlation regression on Wednesday, or maybe just bump that entirely to Monday. So that's our last couple of classes. Final exam coming up pretty soon, so more information about that on Wednesday as well. And as always, if you have any questions, pop in office hours, shoot me an email. Stop the recording.